Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, let's get started. Good morning, everyone. Welcome to the Dr. TLA Plus series. Great to see a lot of attendance here. So before introducing Andrew and today's topic, since this is our first lecture, I'd like to spend a few minutes to cover the series itself. Okay, so we all know that TLA Plus is very effective tools to help us write more robust distributed concurrent systems. And we have been using that in Azure teams here, and AWS has been using that in their services, right? A lot of great results being achieved. So the purpose of this series is to curate more learning materials for the entire community. So all the lectures will be recorded and live broadcasted within Microsoft as well as on the internet, so anyone actually can join this. And before I go a little bit in detail, maybe show of hands, how many of us here have done at least one TLA specification? Great. So for those of you who have done something or are working on that, hopefully this will be very helpful to you. But even if you just started or thinking about starting, I hope you will find that this lecture is also beneficial because we are really trying to shoot two birds with one stone, right? So first one, the first goal we're trying to achieve is for every of these lecture, we'll focus on one distributed or concurrent algorithm or protocol. So the presenter will really go deep inside what, how, and then why of this protocol. So hopefully coming out of the lecture, even without touching the specification part, you will have very good understanding about very well-known algorithms. So that's one part. So the second part is we're gonna spend a lot of energy studying specifications. So I want to make this very clear up front that for the basics of specification, like knowing what is existential quantifier and universal quantifier, this you should read by yourself. But as long as you have the basics, you should feel helpful coming to the sessions. The presenter will share how they understand the specifications, what learning they get out of that. So the purpose of that is it will help us all to write better specifications, right, and then apply to real systems. Okay. And then in terms of schedules, we already have a number of very good speakers lined up. Today we'll have Andrew talk about the Paxos, and then we have other very interesting topics to follow up. So for internal folks, please sign up to the TLA Plus Outlook group. So we'll make an announcement there. For external folks, please sign up for the Google TLA Plus discussion groups, and then the announcement will be sent there. And then the time, we're gonna choose 10 to 11:30 a.m. PDT. That's suggested by Leslie, because this time is still manageable for people in Europe. So we're gonna stick with that time, but then the specific date will announce. Okay, so with that, let me introduce Andrew. So Andrew is a software engineer from Microsoft Azure team. He has been self-teaching himself and then do a lot of TLA Plus specifications. And recently he served as a TA to Leslie Lamport, where Leslie gave a 3-day training to internal engineers. Okay, without further ado, Andrew.
Okay. Switch over the presentation. Okay. So this is on, I guess. We have audio. Is there some way of checking that? Person in back, maybe? Okay. Sorry? We're good. Great. Excellent. Okay. So, welcome to the very first lecture in the TLA, or the Dr. TLA Plus series. This is a series put on by Cheng Wang. That's how you say it, right? Yes. Okay, great. That's right. And the goal of this series, there's a few goals of this series. One is a nice sort of carrot. You get to learn a neat little either algorithm or protocol, usually in the field of distributed systems. 2 is to explore the value of TLA Plus as an actual specification language, because for a lot of these, it's much easier to learn when you're actually looking at the specification versus some like plain English explanation of some very complicated logic. That's what I found. And the third is we'll actually look at some really well-written specifications of these protocols and see what we can learn from them and apply in our own specifications. So that's sort of the high-level goals of this lecture series, and they're also expanded upon previously. So for this specific presentation, here are our learning objectives. These are the questions to which you will know the answer by the end of this lecture. First is, what is the Paxos protocol? What problem does it solve? What applications does it have? You know, it's a really good hammer to have when you're in any sort of distributed systems environment. Secondly, we will learn how the Paxos protocol works in just a very basic logic level, and then far more importantly, why it works the way it does, because it's a really, really simple protocol. Like the most complicated operation is the less than operator, but you'll look at it and you'll be like, well, why are we doing that? It doesn't make any sense, but we'll see all the problems that these little things solve. And third, we'll actually look at the Paxos TLA Plus spec written by Leslie Lamport. It's a very well-written spec in my opinion, and I think probably a lot of people's opinions. And there's a lot you can pull from it and apply in specifications that you write. So first, I'll give you some motivation. Here is the problem we have to solve, or a problem anyway. So in this modern world, banks don't have stacks of cash in like a vault or anything. They have a number living on a computer. That's your account balance, all right? And you don't want this just living on a single computer in case that computer crashes or gets hit by a meteorite, some terrible disaster, because you know that's pretty valuable information to be lost. So the easy solution is you replicate that on a bunch of different computers. And it's very unlikely that all the computers around the world will be destroyed at once. And if they are, we have bigger problems than your bank account balance being lost. So this logical solution gives rise to another kind of much more difficult problem, which is how can the bank maintain consistency among all of these different replicas with your account balance? And at first, this seems really easy. You'll just like come up with something like simple solution, like, oh, just, I don't know, transaction comes in, like withdrawing money, just send it to all the other replicas. Great, you know. But it's really, really easy to shoot holes in that, especially when you're in an environment where messages can be delivered not at all or multiple times. Replicas can crash. They can miss a bunch of transactions, come up again. You have all these terrible, terrible things you have to deal with. And ad hoc implementations will always fail, basically. The general name of this problem is fault-tolerant consensus, which is kind of stated as how can we get a network of processes to agree to a single data value, say like a transaction, like they all agree that there's a transaction, withdraw $20 from your account. And like I said, it's very, very difficult in the presence of faults, like those three that I mentioned. I should also say here there's a fourth type of fault which is commonly analyzed, which is Byzantine faults, which allows for data corruption and also for one of your nodes to be kind of evil and trying to mess up everything. We're not going to be covering that type of fault today. We're just going to be covering these three types of faults. And this is an interesting problem because, like, I mean, what does it mean for a bunch of processes to agree to anything anyway? It seems like a very human thing, and it is a human thing. And we just really just pick our semantics. And here we'll say that if a majority of all these processes settle on a certain value, then that is chosen or agreed upon. And we also run into a very unfortunate mathematical sort of fact about our universe, or just a mathematical fact, depending if you're a mathematical Platonist or not, that no deterministic fault-tolerant consensus protocol can guarantee progress. So no matter how tricky you are with the design of your algorithm to solve this problem, you're always, always, always going to run into some situation where you run into like deadlock, live lock, just you can never reach, I guess, termination. Or yeah, your algorithm can never always make progress. There'll always be some situation where things just go bad. And what separates good algorithms here from bad algorithms is that the situations in which things go bad in good algorithms are rare and unstable, easy to recover from. So an example of an algorithm which has those properties is Paxos. Paxos solves the fault-tolerant consensus problem. It was introduced by Leslie Lamport in 1998 in the paper Part-Time Parliament, I think it's called. There's a really funny story about that paper on his website. Apparently, when it first came out, he went around in like a Indiana Jones outfit presenting the whole thing, like trying to cast it as like he discovered this long lost parliamentary procedure from the Paxos Islands in Greece, and nobody understood it. But funny, I wish I could have been able to see that. Maybe he'll bring it back one day. So anyway, it is reputed to be difficult to understand. This is a pernicious myth. This is not difficult to understand. I promise all of you will understand Paxos by the time you're done with this talk, assuming you paid attention at all. So we will see why it's quite a simple protocol. All of you will be able to take the spec, implement it at home. All right, just dispense with this myth. No, it's not difficult. Something difficult would be like, I don't know, like Schoenager-Strassen or something like that. So anyway, high-level overview. Keep these points in mind just to sort of guide your understanding as we go forward. There is a single elected leader, which we'll call a proposal or a proposer, which handles all client requests. So all client requests go through the leader. If a client request is sent to something which is not the leader, it just ignores it, doesn't even handle it. All right? It is a two-phase protocol. We will separate the phases into one called prepare and one called accept. And it has a really nice property that it can withstand the complete loss of a minority of nodes. So as long as the majority of nodes are all reachable and kind of responding and working, we can theoretically make progress. And we won't have any data loss or corruption or anything like that. But like I said in the previous slide, there's the inherent fallibility of any fault-tolerant consistent algorithm, which is that it can never always make progress. And here, Paxos can become live-locked, and we'll show you how that happens. And maybe you'll figure out yourself before we get to the slide, but don't fill it out. But the state is unlikely and unstable. So really, really nice properties about this protocol. OK, so any initial questions at all like that about this? Seems pretty simple so far. So we have to talk about how this kind of applies to the bank account problem. All right. We have here a sort of list or a log of transactions, like say withdraw $20, deposit $50, withdraw $100. And kind of what we do is for each entry, each transaction, we execute Paxos in rounds. So every entry has a single execution of Paxos to decide what like the zeroth transaction is, what the first transaction is, what the second transaction is. So all of the replicas see the same transactions in the same order. And we can think of each replica as a state machine. If you know anything about finite state machines, you know that if they have the same start state and they're given the same input, they all end up in the same state, right? That's how state machines work. If you design your app this way, and you have this log where every replica sees the same thing in the same order, they're all going to end up in the same state, right? It's really nice. It's a really nice way to think about distributed systems. So again, to reiterate, how this relates to Paxos is we execute a single round of Paxos for each entry in the log. There are more advanced forms of Paxos where they have some efficiency, like multi-Paxos has a more efficient way of doing this where it kind of does a single round for like multiple things in the log. Anyway, we're going to be focused on really basic Paxos. I should say at this point that there are like a whole bunch of variants of Paxos. Like you're doing fast Paxos, I think, lecture in a while. There's like a egalitarian Paxos. There's Byzantine Paxos. We're just doing basic Paxos, a single round. Yeah. So everyone's kind of comfortable with a state machine model of execution? OK. So let's zoom in on a single transaction then. And here it is. This is Paxos. This is the entire thing right here. This is all you need to know. But the way we're going to be presenting this is we're going to have the plain English explanation here, which is going to be very confusing. And then we're going to alternate between that and the TLA plus spec. So we can, it's just like, it's really easy to see what's going on with the spec. But not all of you are familiar with TLA plus, so I'll do a bit more explanation when we look at the spec. Excuse me. But here I'll just like do like the high level over here. Or sorry, the English language overview. So we have the two phases. This is the prepare phase, and this is the accept phase. Kind of how it works is you have your leader, sends out a bunch of messages to all the acceptors, they're called. So the proposer sends out messages to the acceptors. Acceptors respond back to the proposer. And then the same thing's repeated in the second phase, but with just like various slightly different rules. So how it starts out is the proposer leader receives a client request, like withdraw $20. And it creates a proposal just tagged with some GUID n, all right? Just some number. Sends just the message containing that number, like say 5 or whatever, out to all the acceptors. Okay, on the acceptor side, the acceptor receives that message n, and if it's previously seen any proposal ID which is like higher than that number, it just doesn't even reply to that message. And this is where it gets kind of complicated to explain in English. So we're probably going to hop over to the TLA plus spec right now. Okay. So this is the TLA plus specification. So how many of you have like no familiarity? That's the wrong way to answer it because people won't want to put their up hand. How many people have like good familiarity with TLA plus? Good familiarity? Sort of familiarity? How many people have never seen this language ever before? Shucks. Okay. All right. Okay. So TLA plus 5-minute introduction. It's an action language. Okay. We define different actions that can be taken at any state. These actions have a precondition, and then kind of like what the state will look like after the action is executed. Okay. And you usually feed this into a model checker, which kind of does a breadth first search of all possible kind of execution traces, and tries to find places where invariants that you specify don't hold. Does that confuse anyone? I don't know if you've ever seen a language like this before. It's a bit strange, but it works really well. And what we have is 3 things which are kind of like input to the program, or not the program, the spec. We have the set of all acceptors. We have the set of all values from which we're choosing. And then we have the set of all the quorums, so like the set of all the majorities. And here, if we go here, I have an example of what that input will look like. So for values, for acceptors, we just have like 3 values, A1, A2, A3. They're just placeholder values. For values, we have value 1, value 2. The actual value doesn't matter very much. And then we have the list of quorums. Quorums here is just the majorities. This is the list of all the subsets of acceptors such that that subset constitutes a majority of acceptors. Here we see that math is much easier to use than English for explaining these things. But yeah, so A1, A2, A1, A3, A2, A3. Did I miss any? I don't think so. That's all the majorities, right? OK. So that's kind of what that'll look like. Hopping back here. And yeah, we can see here. That's just what I just said, the quorum assumption. I'm sure everyone here is probably familiar with existential quantification. And yeah, OK. Universal quantification. So we say, first of all, quorums is a subset of the set of all acceptors. And for every Q1, Q2 in quorums, their intersection is the empty set. And that's basically what we assume about it. It's kind of difficult because not many people really know about this. All right, anyway, going down to the actual phase here.
It's not. It's not equal.
Is not the empty set.
Not empty.
Yeah, sorry. This is not equal. Yes. OK.
So for folks here who use the vertex, it's essentially the same thing as vertex.
Yeah. This language actually compiles, I guess, to a PDF using LaTeX. It's really kind of a neat feature. But
Lamport all over the place.
It really is. You can see his signature everywhere. This actual specification was written by Leslie Lamport, by the way. This is his TLA plus specification. But all right, enough about that. Let's look at the prepare phase. So what happens is the thing that I talked about before, the leader receives a client request, creates a proposal tag with GUID n, and sends a message, OK? Yes, sends a message to everyone. Oh, are we? Well, OK, I think everyone can read this mostly. Hopping back here, let's see how that compares to the TLA plus spec. So first of all, we just say that don't exist a message similar to the one that we're about to send. So we haven't already sent it, basically. And in that case, we send a message of this type, this type 1A, phase 1A, sorry, and then the ballot number, which is that n I talked about, is also appended to the message. And then the rest of the variables are unchanged. This is kind of tricky if not many of you know how TLA plus works. But here's the precondition to this action being executed. And this is the thing which actually changes. After this action has been executed, we will have added this message to the set of sent messages. Does that seem reasonable to those of you who are completely unfamiliar? Yes? Oh, sure, OK. So this is a modeling language. And for, I guess, simplicity, we were just holding the entire message history, like all the messages we've ever sent in a variable, OK? And that way, we can see, we can have this simple check here to see whether we've sent a message with this ballot number before, because we don't want to have done that. In an actual implementation, you probably won't keep your entire message history. You will have something like, you'll just have like the last ballot number you sent, and you'll pick one higher than that or something like that. So this is a specification language. Specification is not equal to implementation, as I'm sure you're aware, but we can get a sort of functional equivalence.
Condition, this action will happen.
Absolutely correct. Yes. Yes. So in any given state, you'll have some subset of all of your actions which will be enabled, they're called, like we're able to execute them. And then the model checker will do a breadth first search, like non-deterministically run through either of those actions. Sure. OK, I'm trying to compress like a 3-day TLA plus course into like 5 minutes for some of your benefits here. So hopefully this will at least, you can sort of read it, if not write a specification.
But why not go through the English version first?
The English version, OK, this is just my personal experience is that the English version is quite tricky to understand. And we'll see this if we get on to this, because you have all of this that you're trying to encode in English, and it gets very confusing. So what I'm trying to do is to intersperse the English language presentation with the TLA plus presentation. Is that, you would find this approach confusing?
I think that if I can understand the English version first, even missing some corners is better than get all the details. I mean, this is my preference.
Sure, OK.
But the comments are good.
Yeah.
Sorry?
If you keep the comments on.
Oh, sure, yes. Yeah, the comments are a really good like English explanation, I suppose, actually. Phase 1B. We're on phase 1A. All right. Here, something like that. OK. So here we have phase 1A. I should mention we were mostly expecting people in this course to have some familiarity with TLA+. That was the target demographic. So we put quite a bit of effort on, or not so much effort on like the English language explanation. So
this is the first lecture, right? So we have excuse coming here without knowing anything about TLA+. So hopefully next lecture, we should have some preparation before coming to the lecture.
all right.
Because of heads in the way, it's probably best the part you're focusing on not be at the very bottom of the screen.
Because head is in the way?
Because people's heads are in
see
my way.
what's for the phase one. Like the audience
This person's
Oh,
head
it is.
in my way.
I see.
Screw up.
We'll slightly. Is that above everyone's head?
A little higher would be
Okay.
better.
All right. We also see what the send function does. We have so here we have a primed variable. For those of you unfamiliar with TLA+, the primed variable is the value of the variable after that action is executed. So super crash course on TLA+ here. But obviously, so if you send message M, then messages prime is equal to the set of messages unioned with the set containing M. Fairly simple to understand, I think. OK. So I'll just read this English language. Right. Fair number. But yeah, the cup is, yes, union. Union of two sets. So, yeah.
Do you have the PDF of those?
The PDF of this? I could probably generate the PDF. Maybe.
And is tilde like tilde in LaTeX, or does it actually have some kind of meaning?
Sorry?
Is tilde just spacing like it is in LaTeX, or does it have meaning in TLA plus?
The what is spacing? The
tilde?
Oh, tilde. This is not. That's logical not.
Okay.
Yes. Okay, so here's what the PDF version looks like, actually. I don't know if it's easier to read at all. Maybe, actually, it might be easier to read for the people unfamiliar with TLA. So we have send M, messages prime is messages union.
Yeah.
Okay, yeah, because...
You don't have to speak LaTeX.
Yes. Great, so this removes the dependency on LaTeX. What else can we say about this? So this is the first phase. This is just like proposer receives a client request. All it does is it picks some number, sends it out to all the proposers. Does that seem reasonable? Everyone's okay with this first phase. All right, let's move on to what the acceptor does when it receives that message. I'll read the English language thing here first. Oh, great, we start from there. OK, let's not do that then. Oh, OK. What's the actual one to start it from the current? Shift F5. OK. OK, great. So let's look at what the acceptor does then. It looks at that n, which was sent. If it's greater than any ID that it's seen previously in an accept message, which is what we see down here, then it returns a promise, basically, a promise message. And it indicates that it will reject any future proposals with an n which is smaller than the one that was sent. And if it also previously accepted a proposal, accepted is an operation we'll see down here, then it'll include the value that it accepted. And we'll see.
That's the part. If I have accepted multiple proposals, do I need to include all the IDs I haven't seen before?
No, just the highest. Yes. Just the highest one. OK, so let's look at the. Here we go. So you can see this. So we first of all, the precondition for this action is that there exists a message in the set of all messages such that its message type is 1A, so it was sent in the 1A phase. Its ballot value is greater than the largest ballot value that this acceptor has seen in the past, which is represented by maxval A, that returns that value. And if this precondition is satisfied, then it sends a promise message. Here, this is what it sends: a type 1B message, which is the promise message, with a few fields in there. It sends the ballot that it received just now. It sends the largest ballot that it's ever seen. And if it ever accepted a value, then it attaches that, the last value it accepted. And it also just attaches its own identity, just so that we know which acceptor it came from. We also update the max ballot of this acceptor to be the current value that it's seen, because this is now the largest number that it's seen. So any confusion about this? Yes, John?
Max V ballot.
Max V what?
Max V ballot.
Max. OK, yes. All right, so max VBAL, if we look up at the definition, we have the documentation, is the highest ballot for which the acceptor has voted. Where are we saying this? Highest number of ballots. Right. So in the future, in the upcoming part, we'll see like the acceptance phase. So if this acceptor has already gone through like an acceptance phase, maybe it picked up some value there, and that is the highest ballot that it's seen from that phase, which we'll go over in a bit. Yes.
Values, so ballots are these unique IDs.
Unique numbers, yes.
And values are
any value. It could be like withdraw $20, deposit $10. It depends on what your application is.
They have to be ordered.
Values don't have to be ordered. The ballots
You
do.
pick the max value. I mean, you're sending max values.
Oh, sorry. So max vval here, it stores the value associated with the largest ballot. There's not multiple values.
Okay. Yeah,
Yes.
I see. The corresponding
Yes.
values.
Okay. So I think this is getting a bit of a slog because for a few reasons, but let's just kind of like dash through the last two phases, and then we'll skip to kind of, I took the approach of we create our own consensus protocol, and then like we see how it fails, and then we see how we kind of like arrive logically at Paxos, which I think is like a really good way of learning, better than like this, because this is just reinforcing the impression that Paxos is really complicated when it's not. Okay. So in acceptance, we basically do the same thing. The proposer sends out assuming it received a majority, promises from a majority of the acceptors, it sends out an accept phase message containing the actual value that it wants to be accepted. And then if all the proposers, if a majority of those respond that yes, they accept that, then that value is chosen. And once a value is chosen, only one value can never be chosen, and if a value is chosen, another value can never be chosen. So that's kind of like the high-level overview. And now I really hope I haven't drained too much of your brain power and enthusiasm on that. We'll skip to just maybe yet a question of how we actually do leader election.
You are going into details.
Yes. So what we're
phase 2.
You don't have to. The point is, we're not going to do like a deep understanding right now. Maybe we'll come back to this. Everyone's kind of getting into a bit of a slog here. We're going to like try and create our own consensus protocol and see how we kind of arrive at what Paxos does. Does that seem like a good approach to you?
I'll wait.
Certainly.
I've been waiting many years to understand this.
I would be so sad if I disappointed you now. I really want this not to be known as a complicated protocol. But, okay. Maybe some of you had a question about leader election floating around in your heads, but you didn't ask it. I'll just assume you did. Leader election can really be as complicated or simple as you want. The leader election protocol I really like is that you just number each process from 1 to n, and you send heartbeats every t seconds. And if a process does not receive a heartbeat from a higher numbered process in 2 t seconds, it just assumes it's a leader and starts acting that way. Pretty reasonable, right? You can get really complicated with like least-based systems and whatnot, but this is just like so easy. I really like this leader election algorithm. Seems simple, right? Okay. So we will design our own consensus protocol. Yes.
Election, Paxos is not bounded to a specific leader election protocol.
Correct, yes. You can choose any leader election protocol you want, as long as there exists some leader. And you need a leader in order to make progress and stuff. There is also like scenarios where you have multiple leaders. In fact, a lot of the complexity that we just saw was to handle the case of there being multiple leaders to make sure that there's no corruption. Okay, so let's take a good old college try at designing our own consensus protocol. And we'll see how some simple, kind of naive approaches fail. The main point here is we're going to see why Paxos works the way it does. And first of all, we got to define our requirements. What do we want our consensus protocol to do? We want it to be consistent so that only one value is ever chosen. We can't have multiple values chosen. We want it to be immutable so that once a value is chosen, for the rest of all time, that is the value that was chosen. It can never, ever be overwritten. Yes?
That is for a given ballot, right?
For a given ballot, yes.
For a given ballot.
Yes, yes. So this is for like a single transaction, and then like the next one would be like... Sorry, slot?
For the slot.
Oh, yeah, sorry. No. Once a value is chosen, anytime they even try and like send like higher valued ballots, we will still end up choosing the value that was chosen previously. You can never overwrite it.
But how do you update?
You cannot update.
So the point is, so remember going back to this slide. So we run Paxos for every single element in this log, okay? This is how your application would actually look. So you run Paxos here. This is chosen for the rest of time. This is like locked in. If you want to add another value to your system, you'll run another round of Paxos for like a second value. Yeah. So Paxos is like single shot. Once it's chosen for the rest of all time. Okay. Oops. OK, so we want it to be immutable, which is once a value is chosen for that slot, for the rest of all time, we cannot choose a different value. And we also want a nice property of durability, which is why we're here in the first place, right? Because we want to replicate our information onto multiple nodes. And we'll say that we want progress to be theoretically possible as long as the majority of nodes are reachable. And just to simplify things without getting into too much like theoretical stuff, we'll define chosen to mean that it's accepted by the majority of nodes. It's just a nice definition to work with. OK, so does anyone want to like just take a shot of what logic we should put in the acceptors for whether they should accept values? No one wants to take a shot. OK, that's OK. Here's maybe the first, you're a college student looking at this problem, and you're like, well, I'll try this way. We'll just say that there's a single round, and acceptors just accept the very first value they receive. OK? But then we run into this problem, which is that maybe you have multiple leaders, and they all send messages to some. By the way, how to read this diagram? We have these 5 processes, servers, whatever you want to say. Time goes this way. These arrows are messages sent from some like leader to some acceptor. By the way, leaders and acceptors can be on the same process. That's part of the way the protocol works. Does anyone have any confusions about this way of, yes?
In the same server one means it sends message to himself? Is that?
That's correct, yes, because leaders and acceptors can be in part of the same process. Yes. Yes?
I thought it sends the message to all acceptors.
It tries. Maybe sometimes the message fails to be received, which is actually what happened here. Yeah. So maybe we have 3 leaders, and what happens if acceptors just accept the first value is we will never reach a majority. See? And so this isn't really what we want. I mean, we want something to eventually be chosen. So this is obviously rubbish. So anyone have any questions about why this is a rubbish approach? No? OK. All right. Attempt number 2. Acceptors just accept every value they receive. Why not? We'll just go all the way to the other extreme. And we see here that we violate one of our requirements, which is that only one value will ever be chosen. Because we see that we accepted it here, this is chosen, and then later another leader comes along, and it just overwrites what we chose. So we cannot do this. All right. So we've kind of heard about like two-phase commit. We've never really read about what two-phase commit is, but we know that there's 2 phases. We figure, why not add another phase? That sounds like a good idea. So we check whether a value is accepted or chosen before we try and propose that it's accepted. But then we run into a race condition here, because we checked whether it was accepted here. It wasn't. Another leader also checks it whether it was accepted, and then slips in there, and then it gets it chosen. And then this guy comes along, and we see that it was accepted, and then it overwrote what the other one was accepted. So our properties are kind of violated. Yes?
Why not just a lock? So if you see, I say check for this existing, so you say no, it's not existing, so you lock it, and then nobody comes.
Well, how do you lock it? We're back to square one.
For the other, say if you for the first phase, you say
oh,
no.
you're saying numbers.
Yeah.
Great. I like that you're headed this way. That is in fact our very next thing. We're like, well, I think we need some kind of number type system here. I'm really happy you took that approach. So we're going to add proposal IDs. And here it gets really quite complicated, but we've kind of basically arrived at Paxos now. So for proposal IDs, we'll have 2 components. We will have the server ID, and then just some monotonically increasing ballot number. That's a good way to get a globally ordered and unique IDs. Everyone kind of agrees with that, right?
The ID global or local?
Global. Well, I mean, depends how you mean that question.
You have your ID. How do I know the ID I choose next time will be greater than the ID you tried the last time?
That's a good question. So, for example, we have all numbers generated by process 5 will have form 5 dot something, like 5.6, and maybe you can choose it's local. It's globally orderable. There's a global order that you can put. So you can say that maybe IDs of form 5 dot something are always greater than like 3 dot something or 4 dot something. You can kind of pick and choose your semantics as long as they're consistent, as long as there's a global order.
Does that kind of associate with your leader election protocol? Because that basically give a S5 higher priority.
Yeah, I mean, like, it's not really associated with leader election, but it would kind of work the same that 5 would always kind of like be the one that's used. Yeah.
If they are not consistent, your protocol won't work. Because one will be the leader, 5%, 5 have higher priority. I don't know.
Let's see, I'm just trying to disentangle this question. So it's independent of the leader election, basically. Sorry?
This doesn't require leader.
It does not require leader election.
Okay.
In fact, we have like 2 leaders here. We're assuming like a weird scenario where there's multiple leaders, which can happen if, like, as we see here, this can communicate with these nodes, this can communicate with these nodes, but they can't communicate with each other. Their heartbeats aren't reaching each other. So this one kind of just like assumes it's a leader. Okay, and this is a really complicated scenario, but we'll add like, so yeah, we add IDs, like we had this great suggestion here, where, going back to this previous slide, we want, instead of this, so this would come along, and it would see that it has another proposal that it's seen. It was a way of kind of like communicating that we've already seen proposal IDs. And if we go here, we see that, for example, we send out our prepare 1.2. 1.2 is the ballot number here. We'll send it out to this node, this node, this node, and this node. We will receive promises from them. So we've received promises from a majority. We can continue to the second phase. At the same time, we have a second leader here. And this guy also sends out promises here and receives responses from a majority. And then it sneaks in again, like similar to the last slide here. But here we also have proposal IDs. And so we send out the second phase, the accept requests, and they are accepted by a majority. So this is chosen. And then this is the real magic part, which is that this guy finally gets around to sending the messages, and then they're all rejected because this proposal is less than the one that was accepted. So it's similar to, I think, what you were suggesting. Yes. So this is very, very complicated. Anyone have any questions here? Yes?
I'm just curious, for the next round of proposals, prepare messages, does the number, when the probability increasing number be a factor of the previous last node?
The previous last node?
The previous acceptor value.
The previous acceptor value. So I'm not 100% sure I understand.
The next slot.
The next slot. Oh, no. The slots are completely independent. Yes. Completely and utterly independent. Yes. Unless you're using some more advanced version of Paxos, which does some optimization. But here, we're just assuming they're completely independent. So this is like a single slot. OK. Yes?
Why does S2 after it promises 1.2 accept 5.4?
Oh, because just simply because this is higher ranked than what it said it promised to accept.
Might be also helpful to explain that red rejection after that blue promise.
Oh, that's correct. Yeah, that was a large part of why this is complicated because these reach the same thing. This, yes, good spot. So this promised 5.4. It later received a prepare request with 1.2, and since it had seen 5.4, greater than 1.2, it rejected that promise. It refused to promise. But this guy still went ahead because it got a majority, these 3. OK.
And this is actually a two-way arrows, right? Because you
correct, yes, yeah.
One, you also send the receiver actually responded, but didn't show it.
You're correct, yes. This is a simplification. I don't show the messages going back because that would be very crowded. Yeah.
This message rejected because of F5 or because of F4.
Mm-hmm.
So, because like you said, it has more high rank.
and that's why it is rejected.
Mhm.
What rank do you mean? Is it like first 5 or number 4?
Here I'm using the the rank that 5 dot something will always defeat 4 dot something, 3 dot something, 2 dot something, etc.
Just to remember.
Yeah.
Yeah.
Yeah, but you can choose any like total ordering you want, as long as it's like a total ordering.
So this is very important to make sure that the two different guys will never choose the same ballot, right? Because the guy generated 4, the other guy generated 2. You're never sure that you wouldn't duplicate that.
Yeah.
But attach your own ID will make sure that no one will generate the same ballot as you.
Yeah. Just uniqueness of the number that you can generate.
Right.
Okay.
Yes. Yes.
Am I understanding correctly that rejected 1.2 is actually really saying promise 5.4 back?
Actually,
to reject anything below 5.4, so that your proposal of 1.2 is rejected, and anything up to.
Actually, rejected messages are just not sent at all. Usually, they're just not replied. So this, and what that would look like if everything rejected it is this would just never receive messages back from a majority, and it would never continue. It would probably have like some kind of timeout if you were to implement it.
So for cracking this reason, right, you can just silently drop that message. For efficient implementation, you might want to set an active acknowledgement for that.
Okay.
Yes.
So if the node ID is the most important part of this, then now all the nodes will reject anything from nodes 1, 2, 3, 4, because node 5.
No, because node 5 is the highest.
All the outliers, the other ones.
That's correct.
As far as the concurrent, I think so.
Only if node 5 is a proposer in that.
Okay, so in the next slot, it will be, it might be different.
Let me think here.
If 3 had accepted 1.2 before.
So then, if you swap the orders, if you put the node ID at the end, and then use the number, so it will still unique, then you can avoid that problem that some of them get the favor treatment.
That makes sense, but I wonder if you're using this order, then...
Yeah.
You know, actually, I think you're right. Because then, like, if 5 died, then like we would never be able to make progress. Yeah. Sorry, I can't. I'm so sorry to have misled you. The numbers, the prefix numbers, are used to break ties. So if you have a 5.4 and a 4.4, 5.4 is going to win. If you have a 5.4 and a 4.5, 4.5 is going to win. Yes.
Okay, so
Yes.
that's the last.
Sorry. It's a very, very bad sin to like mislead your students because then it's extra. So I'm sorry about that. Yes. So they're used to break ties. Okay, this will make a lot more sense. Yes.
When you find your total ordering, it seems that will be helpful for the audience to know the total ordering that you're proposing.
The total ordering. Yes. Okay. I don't know if like.
Pairs, but yeah, red.
Lexicographic pairs. Yes. Yes. Okay. So it looks like maybe I can just write the code on the board. Will the camera be able to see that? So we have our, I guess we have.
A little lower. Yeah, this is a perfect spot.
Okay, so.
A little lower.
So we compare like greater than
Yeah.
with the greater than function, which is okay. So this will turn true if a actually we'll make greater than equal. We'll say greater than equal. Okay. This will return true if a is greater than or equal to b, where a and b are like 5 dot blah 3 dot etc. Okay. So we will say. I'm writing this code on the fly, so here we go. You guys just get to see. I'll say we have the ballot number and the node number, node ID. Sure? Okay. So if a dot ballot is greater than, actually it'll never be equal. What am I thinking? Well, okay, okay, sure, it's equal. Yeah. If a dot ballot is greater than b dot ballot, then return true. And if a, yes, if the ballots are equal, return a dot and if, yeah, else false, return. Or sorry, if they're completely equal, then
Equal in the
yeah,
yeah.
You're right. That would make sense. Okay, and then just return false. Okay, so this is the ordering function here. So if the ballot number is greater than the second ballot number, then it always wins. We break ties using the node ID. Otherwise, it's false. Okay, I think that's good. Any other questions? Good idea defining the ordering function in code.
Just curious, so for the ballot number, how does each node choose which ballot number to use? In this case,
Very good
one
question.
choose 4, what does one choose 2?
Very good question. So each node will maintain is part of its state, the last ballot number it sent, and then if it fails, it just increments that ballot number, just continually incrementing. A sort of unstated requirement I've held so far is that the ballot number is held in sort of cold storage. So if a node dies and comes back up again, it's able to retrieve its last ballot number, so it doesn't reuse old ones.
That's it per account in this case.
Sorry?
Is this ballot number used per account in this case? So you're depositing and withdrawing money, or is it global for all requests?
It's per slot. We're deciding on a single slot. And by the way, the very simplified bank account model I'm using is there's only a single bank account. Yes.
The last question I had was, is there any compare and swap semantics in this? Or
Any sorry, what?
compare and swap, like knowing what the previous value was and then modifying it.
Knowing what the previous value was and then modifying it.
Compare and swap. Like,
No, it does not
if you
do
had
that.
zero
Oh, compare
dollars
and swap.
Yeah.
No, basically. There is one last thing, which if we're good here, I'll continue with this. We want this guy, the acceptor who sent this, we want him to be able to return to his client the actual value that was chosen. And so
one question from online. What's the difference between ballot numbers, node IDs, and proposal IDs?
Oh, okay. So node ID is just an ID given to each node at the time that the system started. Ballot number is a number which is kept and incremented as proposals continue. And when you stick them together, you get the proposal ID. So I hope that answers that. Okay. Yes.
How does each node know what its quorum threshold is? Because earlier you said that rejections don't send messages back.
Yes.
So what's the technical difference between a failure to receive a message and a rejection?
The technical difference between a failure to receive the message and rejection. There isn't one if you use a timeout. So if you haven't, say, received a reject message within a certain amount of time in your implementation, then you count it as a reject message. But each, sorry?
Back as a reject?
It could or it couldn't. Either really works.
I'm just wondering how it will know how many.
Oh, it starts out that way. Each node, so we start out, Paxos, with each node knowing about all the other nodes in the cluster. It knows how many there are. It knows how to communicate with them, stuff like that. So.
In practice, when a rejection happens, don't you actually send back what your highest promise or your current promise is?
Yes, that is an optimization. So you can fast forward your ballot to match the current proposal ID. It's an optimization if you, yeah.
I think that you should consider 2 to be a ballot number, because ballot number would be 1.2 or 5.4. I would think of the number .2 or .4 as a sequence number. It's part of the ballot. The ballot is the whole thing. What you were calling the proposal ID.
That's a good terminological difference, yes. We should probably refer to the small number as a sequence number, and the entire thing is a ballot number. So it more closely conforms to our TLA plus specification. That is a good point, yes. Any other questions here? Yes.
Yeah. What happens if some part of nodes doesn't reply? So we are not really sure if they not agree or they are dropped off the system at all. So like the effective number of quorum will be less than the one when the system started, right? So how do you deal with that situation?
So this is kind of the situation in which a node dies, you think?
Yeah.
In the event that
several nodes dies, and we assume we have 5 nodes out. In reality, we have just 2 of them. And
if there are just 2,
struggle with
yes. If there are just 2, then we can never have majority and we can never reach progress, or we can never have progress. We need the majority of nodes in order to make any progress at all.
Yeah. How do you deal with that?
How do you deal with that? Usually, if you get to the point where like the majority of your nodes die, you kind of need to perform manual intervention at that point.
Yeah, but how do you know if they die or they just respond to your proposal?
I love this question. I love this question. There is no theoretical difference between a node dying and not replying to a message. It is the exact same thing.
Yeah, but you rely on the total number of nodes for your quorum decision, right?
Yes.
And if nodes die, you cannot rely on their decision in this case. And you do not really know if they died or just do not reply to your message, right?
Yes, that's correct.
Difference to that.
Yeah, so you will never converge in this case, right?
Does the protocol allow you to make no progress, right? It's no guarantee you
Yes.
don't have enough.
Yeah, so this is one of the cases that we will have no progress.
Yeah.
Correct.
So failure detection can be independent of the problem, right? So you have another layer which does failure detection and says whether that.
Yeah.
But you have to have the core in order to make any progress.
That's correct. Yes.
So as soon as the node accepts, then later on cannot reject. Even though, for example, we had received this 1.10.
Yes. It would still be like, I've already accepted a value. Well, so that's actually what we'll get into in the next slide, all right? Okay, this isn't the full story just yet. There's one more component that we're missing, which is, yeah, so say it sent out 1.10 here. It says 1.2, but whatever. This actually, sorry, I'll go into the next slide here. Right, so like you said, so we accepted 5.4. What if this guy sends out 1.5, all right? What happens is this accepts, or it sends back a promise that it will accept proposal of 1.5, but it also sends with it the value it previously accepted. And then this proposal, or proposer, just overwrites the old value, or like gets rid of the old value it's trying to propose, and it just adopts instead the value that was returned. So this whole thing converges to just the value that was chosen. So in the future, if like maybe way in the like 10 years in the future, suddenly like node 2 comes along and it tries to like overwrite the very first transaction in this giant log of account transactions, and it uses like 2.100 or something, it'll still converge onto or deposit $10. So that's how we get our like once a value is chosen, it can never be overwritten kind of guarantee. Does everyone sort of get this? Yes?
It might be helpful to explain that that accept originally tried to do deposit 10, and then you replace it, right? That's what
well, it used to be withdraw 20 actually. So if we look here, this one's trying to forward the deposit. It wants withdraw 20 to be the value chosen here. But it's just like, well, we can't actually do that because we've already chosen deposit 10. So it starts advocating for deposit 10. And then in your bank account implementation, you would probably take like the withdraw $20 that didn't go through and put it into the next slot or something like that.
What's the message in 1.5?
What's the message in 1.5? In the prepare phase, all we do is send the number. That's all. Yes.
Okay.
We send the number, and then if this node has previously accepted a value, it returns a promise and then also the value that previously accepted. So we can kind of like all converge nicely onto a single value. All right, does anyone have any questions here? Okay, now we get to the really, really fun part. First of all, I want to like open the field here. Can anyone think of how we get live locked here? Does anyone know?
I mean, you have an even number of nodes, it could cause a live lock due to no one has control. But that's not live lock.
That's more like that. Like that. Yeah. Yeah.
Something. Should we look to modern political And having pluralities but not majorities?
Not quite, not quite. It's not quite that. I mean, it isn't that at all, actually. But does anyone know? It's a live lock. I'll give you a hint. Yes?
If you keep accepting, or you're receiving things faster than you're accepting them.
Receiving things faster than you're accepting them.
Higher numbers prevent older ones from getting accepted.
Ha! Yeah, it is kind of like that, actually. Yeah, it is. And what we need in order to lead to that scenario is something called dueling leaders, where you have two leaders and they can't talk to each other. And yeah, they're both getting promises and before they can actually accept it. So this guy sends out prepare 1.1. Here we get promises. This guy sends out prepare 5.2. We get promises. This is rejected, so it starts another round. But right after it sends out this prepare, the other leader comes along. It sends out its prepare, and it gets rejected. So it starts like another, or sorry, it starts another prepare. It goes on and on and on. This is the dueling leaders. You kind of see how this works? Okay, there's absolutely no way to avoid this. And no matter, like I said, no matter how we design our consensus protocol, you're always going to run into a situation like this at some point. The really nice thing about Paxos is that this is obviously a very unstable state, right? Like if this guy managed to sneak in here, then we just like, it works, right? So you can add things like randomize timeout, or like, yeah, you can like randomize how long you wait in between failures and retries, stuff like that. So it's very unstable. But I mean, again, even if you add randomized noise, it's possible the randomized noise on 2 leaders exactly lines up. And so for all eternity, you cannot make any progress.
Failures are problematic because
this is where Byzantine failures are problematic.
Because then if I'm a malicious node just trying to make sure nothing gets done,
oh, yes.
I send out 3 promises out of 5, and then I send out with a higher, and I keep sending out, but I never try to get anything accepted.
If you want, yes. If you're a malicious node user and you manage to get control of one of these nodes, then you can make sure that no progress is ever made, basically, by like live locking the whole system. So. Yeah, exactly. Yeah. You could just be like, no, I've totally got like promises from all you guys that you'll accept this value, and then you just like don't even bother with a prepare phase and you just overwrite. So yeah, Byzantine failures. There's Byzantine Paxos, which defends against this. I'm actually not personally familiar with it, but I know it exists. But we're not dealing with that in this model. We assume that all of these are very trustworthy.
This model becomes very unstable because just one node can actually disrupt the whole system.
That's correct. But we assume each node is correctly executing the protocol. So it would also have like randomized timeouts and stuff like that. So this is where you control all the nodes in your data center, basically, and which is.
You assume all the nodes are benign to
yes.
the same
So this is the brain of the distributed systems. We don't want that part to be hacked. That's for sure.
Yeah. So when you get into something like Byzantine consensus, you'll probably use something like, I'm sure many of you are familiar with like Bitcoin and how that works. So they require computer power to they require you to compute some really expensive things basically in order to send these proposals. So you can't just spam it. That's kind of how it works. Hand waving so many things, but yeah. So that's what happens when you can't trust the other nodes. But here, this is for your own internal systems, you can pretty much trust the nodes. And if one of the nodes is acting up, you can probably just shut it down. So, any questions at all? Any I guess I want to take an informal poll. Who here thinks they basically understand Paxos at this point?
Can you go back to the English report?
Actually, yes, this is great. This is great, yes. We'll go back to the English language description now with our hard-fought knowledge where we invented our own consensus protocol, and we see just yeah, obviously it works this way, right? So to restate, we have the prepare phase and the accept phase where the proposer sends its ballot number, and it sends it to all the acceptors, as many as it can reach. The acceptor, if n is greater than any ID seen previously, it's yeah, sure, I'll accept if you send me and accept it. So it sends a promise message. And also, note here, point 3, if the acceptor previously accepted a proposal, it includes its ID and its value in the message. That's how we converge, remember. So that seems familiar to everyone, I think. Okay, and then in the accept phase, the proposer, if it receives promises from the majority, then it either uses the value that it was advocating for, or it abandons that value for a value that was returned in the previous phase. And then it sends out accept requests to all the proposers. And if the majority, and then here on the acceptor side, it accepts it if and only if it has not previously received a promise, or promise to, if it has not previously sent a promise for a higher valued ballot. And then if the majority of acceptors return an accept message, then that value is chosen. Yes?
The second bullet under acceptance.
Here, if any acceptors return previously accepted proposal. Yes?
Its value overwrites. What, can you expand the pronoun its?
Sure. It's so the value returned by this one.
Wait, what if I get 2 accept responses back? Which value overwrites?
So you mean 2 accept responses with different values?
Yes.
The one with the higher ballot number.
Yeah. It'd be the one with the higher ballot.
Yeah.
Which is guaranteed to always, there'll always be one which is a higher ballot.
Okay.
Yeah.
That's fine.
Yes. It's true. It's very difficult to concisely say this stuff in English. There's lots of little things, which is why I like the TLA plus specification.
This is basically saying it's a single transaction. And if everyone has, majority have accepted the proposal before, then I won't change the value. I'll just give up, I override the value.
Exactly. And then it's up to your system to determine what you want to do with that value. You probably put it in another slot. Yeah, like the next slot.
How do you enter a new transaction?
Enter a new transaction? Oh, that's kind of more on the implementation side of things. You would have, you would be like, okay, your system would be like, we tried to execute Paxos for slot 0 with deposit $50, but it didn't work. So I'll just pick slot 1 and try for that, and then so on and so forth.
But how do all the nodes know I'm entering a new transaction? Because that's also a consistency, right? If I think I'm still in the previous transaction, and you think you are entering a new transaction, that will break.
As part of the transaction, as part of your validation node, you probably also would send out the slot number, and then each node would have they would have a list of every single ballot and value they've accepted for each slot. You kind of see how that works. Okay.
For the same slot, everyone has to do the same thing, right? That's just guarantees consistency.
Yeah, but then how do you enter everyone saying, I'm getting a new slot? Because once you are in a new slot, in the first phase, you wouldn't return the previously accepted proposal, right? That previously accepted proposal is bounded to your current slot, right?
Only the leader can go to the next one.
So just for multiple slots, just picture the same protocol, but with every single message you send out, you also send out the slot number, like the slot number to which it refers. And each slot is completely independent.
And the only leader move ahead the slot number, you'll say.
Sorry?
So even for the other guys, after you execute slot 0, you're going to execute slot 1, right? If you don't know what is in slot 1, you run the protocol, you'll find out.
But who moved the slot number?
So the slot numbers go on independently at the same time. So you don't move from slot 1 to slot 2. You're always in slot 0, you're always in slot 1, you're always in slot 2, you're always in slot 3. You're just independently running these protocols. You don't move from one to the other.
But what do you mean I cannot always be in multiple slots?
You're always willing to accept a message saying this message is about slot 5, this message is about slot 1, this message is about slot 2.
So, but who picks the slots?
I think there's a slight confusion as to what slot actually means. Slots don't change in time, right? Like you don't go from slot 0 to 1 to 2 to 3 to 4 and so on, right? They're just independent buckets that you can put things into.
That's correct, yes. And then, but what your state machine, we expect it to execute the slots in order. But I mean, I could start picking or deciding something for slot 100. I mean, I could do that.
You can't withdraw 100 or close to the 50, right? You go in order, right? So,
yes,
this is
there's a precondition, right? At that state, you have to check.
No. So sorry.
Let's put it this way. Okay. So you are a state machine start from scratch. Okay. You're always gonna try to figure out what is slot 0 for you to execute. How do you find out? You run this protocol, you will learn what is in slot 0.
But what if everyone is trying to decide slot 1, nobody picks up slot 0?
In that case, is pre-agreed, right? So let's say all these nodes agree that everyone will start from slot 0.
Can I give you an example?
How do I know slot 0 was a fixed, I shouldn't move on to, but...
Yeah, can I give you an example how you'd solve this? So for, say you receive a client request, all right? You try and execute it for slot 0. You see this chosen. Okay, go on to slot 1. Okay, it's chosen there. Oh, you go into slot 2. Okay, it's chosen there, etc. Until you find a slot where it actually goes through. Yeah. And then on the state machine side, you only execute like slots, like the contiguous slots. So if you have like 1, 2, 3 chosen, there's a gap at 4, and then 5 is chosen, you still only execute the first 3 until 4 is chosen, and then you like go through.
Okay, so slot would become part of your message.
Yes, exactly.
Slot number.
Slot number becomes part of your message in this implementation. Yes?
So what if we have the majority accepting this proposal phase, and then in the accept phase, the majority doesn't accept, but some of the nodes just accept. So those nodes that accept won't change, won't accept any further requests, right?
The nodes that accept a value, they will accept any higher valued accept message. Or like
higher value.
Yes.
Okay.
So this is where we get into like a malicious node could just like overwrite everything, but we expect it to, if the proposer receives a value in the prepare phase, it uses that value in the accept phase. It like dispenses its value it was trying to. I don't know if that answered your question. Okay. All right. Any other questions here? Yes.
So does each slot has to be chosen first before moving to another slot?
Not necessarily.
So for banking example, then it's a poor choice, right? Because you don't want to make your balance to be negative, because say I have a withdraw $100 in the second slot.
Yes.
And I in the first slot I say add $100 and I started with $0.
Okay.
Right? So if I do second slot first, my balance becomes minus $100.
A lot of banks do that. So
you always wait till you know what's the decision of the 0th slot.
That's what I was asking. So do you do it in order, or can you do it out of order?
I mean, it depends what semantics you want in your system, really.
This is where the paper Paxos made simple also breaks down and it becomes not simple because it keeps talking about slots and skip a slot and no one comes down.
So
it's all simple until the slot thing.
You find the slot thing hard, okay.
Yeah. Because certainly this has to happen in the time series. You
yes.
21st, then
yes.
you positive.
Okay.
You know,
yes.
There's a time element.
So there's a really good paper called Ordering Events in a Distributed System, which, I mean, like, it's kind of impossible in a system to say a lot of the time one event happened before another, unless you have some kind of communication there.
Here's the assumption you have a single client, right? What if I have a multiple clients submit those transactions in parallel, or that can arrive at the destination?
You can actually do parallelism. You can decide like 0 and 1 at the same time, independent of each other.
Right. In that case, that order really doesn't matter, right?
You have 15 minutes?
I have 15
Do you
minutes, yes.
comment?
In the English description, in the third bullet of the 2A, can help you.
Sure.
You said the proposer sends an accept to request all proposers.
It should be all accept.
Yeah, all accept.
Oh, did it? Oh, geez, sorry. That's a typo. Oh, yeah. That is indeed. Sorry for the confusion. All right. Anyone have any sort of questions about this? We'll be now moving on to the sort of, excuse me, TLA plus heavy part of the course, which I've kind of avoided so far because not a lot of people know it. So if anyone is intimidated by TLA plus, maybe this won't be like that useful to you, but you're welcome to stay anyway. So let's see. Right, so we'll look at the TLA plus spec now. And the highlights here are that we look at the like the phase 2A definition is just like, I think it's pretty incredible. And also, when you talk about invariance, we'll look at consistency. I'll just like show it here. Okay, where's phase? First of all, let's look at consistency. Consistency, yeah. For every v1 and v2 in values, for any two values, if one value is chosen and another value is chosen, then they must be the same value. This is the sort of, isn't that like a beautiful invariant? Like that, you can just write that in this language and it checks it. It's wonderful. Yes.
So, is there anything special about Paxos? Is Paxos the best optimized protocol for achieving those properties? Or is this one of the possible protocols?
Can I suggest something? So let's go through the TLA part and then we'll cover those questions again. Right?
Sure. But it is a good question. All right. So this is an invariant that you can check in every single state. We can check that if two values are chosen, then they must be the same. It's very pretty. I mean, like, yeah, it's pretty good. Okay. What else should we look at? Right, the phase 2A. Phase 2A. This is quite complicated. Like I can picture myself trying to write this in TLA plus, and I would use a bunch of like let in and like choose and gross stuff like that. But the way that this was written, I think, is really, really good. So we just say that first of all, the precondition here is that there exists. Where are we? Right. So there does not exist any message that has been sent already. We basically have not sent a 2A message with this ballot number yet. So like, we're not just repeating this step. Okay? And so we ask whether there exists some v in the values and some quorum, and such that we received a, how can I explain it? Maybe it's like, I'm just trying to translate this back into English. Maybe you should just look at it. All I'm doing is just like reading math at you. But really, there are kind of just like two different cases here, which is that here, so we've not, right, here, we've not yet accepted any ballot number. Yes, -1 is like the flag where we've not yet accepted anything. So that's one of the cases, in which case we just return a promise request with no value in it because, yeah, that's just kind of what you do. And then the second case is, I'll move this out of the way, is that we have actually accepted a ballot number and value, in which case we return that value there. This is 2A.
2A, you have overreached.
Oh, this is 2A?
This is 2A. You're showing.
I'm at 2A. Oh, shucks. Oh my gosh. I'm sorry, this is very confusing to people here. Right, phase 2, phase 1B. Right. Yeah. Okay. Right. So this is back on the proposer side of things. We've received all the messages back, and we want to know whether we should keep our value or dispense with our value and use one of the accepted values. And that's what these two cases are about. This case and these two. So this is one case, this is another case. For those of you not as familiar with TLA+, the up arrow is and. You can have like a bulleted list of ands, that's a conjunction, and then the V is an or. So the bulleted list of V's is or. And we have non-determinism here. Well, we don't really have non-determinism. Anyway, I won't go into that actually. So this is, I think, if you're thinking about how to encode really complicated logic in TLA+, you should probably look at this action for, I guess, inspiration. I was recently specifying an elevator system in TLA+. By the way, if you've ever looked at an elevator system and be like, oh, this is simple, I could do that, that's whatever, elevators are rubbish. Like, just try and write your own elevator system. It is not easy. So some of the logic gets very complicated, and looking at this action really helped me out in like encoding really difficult sequence of logic into a nice kind of mathematical, statement.
Change the value. in this
Okay. That's a good question. So it would be such that C max value is B. You choose so you choose a V in values. It comes like all the way back here, basically.
Okay, I see.
Where if the value
has those properties.
If the value is returned, then you use that value. Otherwise, you can use the value that you previously were sending. Yeah.
The second case, not the second case where we are looking for a valid. The first. Where is the requirement that S be a quorum? Why can't S be?
Where is the requirement S be a quorum? There is.
In the first case, that's.
Yes, for here.
That's the end.
For all A in the quorums, there exists a message in this subset. This is another See, if I were to just come along, I would probably write this differently, and I don't think it would turn out as well. This is, I think, this shows a kind of a way of thinking that it's difficult to sort of describe. I probably wouldn't write it this way, and when you look at it, it's like some kind of alien wrote it, and sorry if Leslie's listening here. Sorry for calling him an alien. Okay, yeah. So this is, I think, a really good example of an action. Yeah. Okay, I can run a model check. I was in the process of specifying a model check here. I had to. By the way, notice. So one thing we run into here with model checking is that this ballot number is monotonically increasing. So this number of states in this system is infinite, basically. So what we have to do is we have to artificially restrict the ballot numbers we can come up with. And the way we do that is by redefining the natural numbers as the set from 1 to, say, I don't know, 5. So that's how we do that.
This proof is bounded by the number of nodes we have.
This proof is bounded. So here's how should I say this?
My ballot number is limited and I have a lot of nodes. Then things you can prove will be different when you have a large number of ballots and you have smaller nodes.
So now we get into the difference between model checking and formal proofs of correctness. Because model checking is good to make sure that your system holds under probably 3 nodes and 2 different values. Something very small because you have combinatoric explosion of state, and if you add too many more than that, it becomes you spend days running the model checker. Exactly. You can find a counterfactual with model checking, but you cannot prove that it's correct for all n or whatever. However, TLA Plus does in fact have a proof system, which we can see at the bottom here, which does actually, you can prove things for all n and stuff. Where do we go? What's it look like? It looks like this, right? This is a formal proof of correctness of Paxos. I'm not really sure what properties are being proved here, actually. But there is a TLA Plus proof system. I've never personally used it. I find model checking suffices for most of my needs. And also, it's really nice how they work in synergy. So you say you come up with some theorem you want to prove. You probably want to, it's before you spend all this time checking it in a machine, or proving it in a machine-checked way, you just model check it on a few, 1 to 3 or something. So you can know whether it's true or not before you spend all this time disproving this random theorem you come up with. So this is kind of what a proof looks like, all right? We're not going to go into it. If you want to learn the TLA Plus proof system, I think it's a pretty neat proof system. But yeah, we're just going to focus on model checking.
No, let's not go there.
Yes, I will not go there. Don't worry. But model checking, I think, is outstanding.
Here is even if you have very complicated bug, it can be reproduced to use a very minimum setting, and as long as that setting is covered by the setup of the model and model check.
Yeah. And there are a few papers.
Opportunistically, you could use model checking to identify, but not guaranteed.
Well, it exhausts all the states, so it will find them.
Assuming that your
No, it
model
did not
is
exhaust all the states. It exhausts only a subset that you specify.
If your model is not too large, it will exhaust all the states.
If you, yeah, so for example, if we were to use, it's a model, obviously. All right, yes?
Random question. So let's say you've proven your model, everything looks different here. Looks great. Is there any way to generate code from this model?
Yes.
Separately re-implement everything on the side, because that's where the majority of the bugs
Yes.
are introduced.
So there is no current way to prove any correspondence between your TLA plus specification and any code that you generate. There's no way to do that at this point. And it's difficult to say whether there really could be. I mean, I guess there would be, but you probably have to write like your TLA plus in a really idiomatic way. And so pluscal is just a variant. It transpiles to TLA plus, and it just kind of looks like pseudocode, but as no. You can't run pluscal as like actual executable code. You transpile it to TLA plus. It's just like a different way of writing TLA plus. For people that are more comfortable with an imperative model rather than the functional action model which TLA plus has. I personally like TLA plus, not pluscal, but it's a preference thing. Yeah, for actual experience using the model checker and such in an actual corporate environment, Amazon wrote a really good paper. Their experiences using TLA plus at S3 and other stuff. They found like some bugs that required execution traces of like 18 different things to happen, and then they reached it. And so it's pretty cool. I think it's like a really good testament, probably. And there are, I think, probably people in this room are in fact using TLA plus in their systems. And I've personally used it in a few projects, and it's brought me a lot of value. Anyway, let's get this model checking on the road here. This isn't going to. I'm just going to see how like well this model checker runs. Like, see, even with the very small number of, like, we only have three nodes, 2 values. Like, this is already extremely large. Let's see. We'll let this run for maybe like another few seconds, and then we might have to go back to like a single value or something. But yeah. So this is kind of like the smallest possible value with. What property? Right now we're just checking safety properties. We're just checking that the consistency holds. That's all. If this works, I want to add the temporal property. I don't know if any of you know much about like temporal logic, but you can say things like, this will eventually occur. Like, we will eventually choose this value. And what I really want to show with this model checker is that we'll get the counterfactual, that it'll find the dueling leaders thing. And it'll be like, no, we do not eventually find this. But I'm going to decrease the number of natural numbers even further here. And maybe this will help. So we also have a distributed model checker. It like spins up a whole bunch of nodes in the cloud, and you can run it on there. It might help for very large models. Oh, here we go. OK, great. So everything held. That's OK. We just have to come up with a nice way of saying that a value will eventually be chosen. So I guess like there exists be in value such that is it values? Usually we use like single thing per se. It's values. OK, that's a different. OK, so such that yeah. So we want to wrap this whole thing in like an eventually thing. So eventually is the diamond. So there eventually exists v in value such that chosen v. OK. And this will actually probably fail because I don't think we specified. Well, OK. Also, it might fail for a different reason because we haven't specified something called like fairness. There's this additional thing, but whatever. We'll run it and see. Yeah. OK. Temporal properties. Oh, maybe it found the dueling leaders. I guess fairness was already. Let's see. OK, no fairness. All right. Anyway, let's look at what happens here. So we see that let's see, temporal properties were violated, and this spits out an execution trace. This is the sequence of steps that we go through, and then we eventually reach some like deadlock state probably. We reached the end of the natural numbers, and we'd not yet found, or not yet chosen a value. So let's see here. We start out with our initial predicate, where everything is set to -1, basically. And we execute the phase 1A action. And at this point, messages has the phase 1A ballot number 1. Then we execute we execute phase 1A again. So in this case, we have phase 1A ballot 1 and then phase 1A ballot number 2. So we're kind of executing, we're already going into the dueling leaders here. This is kind of, we don't explicitly have leaders in this model, but by virtue of being able to execute phase 1A multiple times, it's kind of like having multiple leaders.
Nothing but send phase 1A messages.
Yeah. Okay, so going on, we have, okay, phase 1B, great. So now we're applying. And we have our messages as, let's see, max vval is 1, max val 1 type. Okay, so ballot, yeah, so we replied to ballot number 2. Okay. And this is phase 1A again. Where at the end of it, oh yeah, we use ballot number 3. Okay. And this is phase 1B. So this isn't really, did we actually find, I guess we found sort of dueling leaders. Yes, yes.
This doesn't even, yeah.
Let's see. If we go all the way to the bottom.
This doesn't even model proposers as distinct.
It's stuttering, so.
Yeah. It is stuttering, okay. Yeah, it is stuttering, I see actually here.
Here the ballots are just integers, right? They're not even proposal IDs. There's no notion of proposers being distinct.
That's correct. Which is like, which is okay actually.
It's just a leader, it's just
yeah.
leader doing themselves.
Type 1B, ballot 3, acceptor. Okay, I see. Maybe if we increase the number of, would increasing the number of natural numbers help us find dueling leaders?
I think you probably also get into stuttering.
Yeah.
We had famous conditions.
This is essentially as close to dueling leaders as this model can
Yeah,
find.
this is as close to dueling leaders as the model can find, you're correct. You kind of have to like squint and look at it, but it is, in fact, dueling leaders. Okay. So this is, let's see if we can go like, just try it with 1.4. Do we have any, we're a bit over time, I guess?
I think so, yeah.
Okay.
You can wrap up.
Wrap up, okay. Well, for those of you that don't really know TLA Plus very well, when you came on here, I admire your courage in sticking out the class. I made it a bit less TLA Plus heavy than it probably otherwise would have, but this is good learning for the future that we can't always expect people to really know that much TLA Plus. I hope that all of you kind of have a pretty good understanding of Paxos to the point where you might be able to go and implement it, maybe. Implement it without slots. I implement a single round of Paxos. I bet you could do that. And I've hopefully dispelled the notion that it is a complicated and difficult to understand algorithm. I don't know, maybe? What do you think? Yeah? I mean, there's not even very much math there. It's just like there's a greater than operator, and that's about it. So, well, thank you very much for attending. And